Hello, students. Hope all is well. I am recording a short instructional video here to show you how to study the six-membered ring with a ball and stick model. Now, normally, I request that students purchase the ball and stick model for use in organic or borrow it from a student. Obviously, you're taking the course online. It may not be possible, and I don't want you spending an excessive amount of money, particularly when things are very difficult right now for many families in our country. So I have uploaded an instructional video already on cyclohexane, where I used Sci-Gress, a chemical platform, to illustrate certain features of the cyclohexane ring. I'm going to try to do it with the ball and stick model now. When we get to stereochemistry, which is chapter 5, I think, I'll show you how with toothpicks and 4 different colored gumdrops you can tackle that chapter. But for now, I want you to do your best to try to look at this video, look at it a few times, and after study, hopefully it'll fall into place. And then you can contact me during e-office hours, and we can go over anything you want as a group or individually. Okay, now listen very carefully to this. The 3, 4, 5 rings are introduced in chapter 3. They occur in nature. The 2 most important and most common rings, and I'm talking about allocyclics, cyclic hydrocarbons, are the 5 and 6-membered rings. In DNA and RNA, the sugars are often presented as 5-membered rings, and steroids contain both the 6 and 5-membered rings. We can use the 6-membered ring as a very powerful pedagogical tool to help you learn the importance of shapes or conformations. I have the ball and stick model, and you're looking directly down at it. I'm using an overhead camera. I'm going to move this over. Okay. There's a bit of a reflection, but what you have right now are above 6 ivory-colored hydrogens and 6 black atoms representing the carbons in the ring, sp3 hybridized carbons. Now this is a planar ring. Let me turn it this way. This ring is planar. So what you have, if we did a Newman projection on these 2, this one and the one behind it, if we were to look at this one and this one, and put one in front of the other, you'd have a Newman projection, and then you would have torsional strain between the 2 sigma bonds and steric strain between, in this case, the hydrogen here and the hydrogen there. Now, the angle of a planar cyclohexane is 120 degrees. And you know and I know that sp3 hybridized carbons want to be 109.5. So there's angle strain, torsional strain, and steric strain. Now, as you replace hydrogens with alkyl groups, methyl, sec-butyl, T-butyl, that's going to become more and more of a problem in terms of steric strain. The most common shape or conformation of cyclohexane is a so-called chair. You prepare the chair by grabbing alternating hydrogens, 1, 3, 5. 1, 3, 5. In other words, if that's 1, this is 3, and that's 5. Bring them towards you. When you do that, you now have a chair. And I'm showing it to you sideways. You're looking straight down at it. And that is a chair. It's called a chair because it looks like a chaise lounge. But you can see we've alleviated angle strain. The internal angle is 111 degrees, pretty close to 109.5. You have 6 equatorial positions. 6 in the equator, so to speak. You have 3 axials, 3 above, 1, 2, 3, and 3 below, 1, 2, and 3. Let me grab these. 1, 3, and 5 below a tripod, 1, 3, 5 above. It's sitting right now on the 3 axial hydrogens. So right above we have 1 there, 1 there, 1 there. Those are axials. Now as we replace hydrogens with alkyl groups, we're going to have what are called 1,3 diaxial interactions. In other words, here, here, and there. They're going to converge. So there's a trade-off. The ring, by going to chair, probably the most common conformation of a 6-membered ring is a chair, not planar. Are there any planar ones? Yes, but they're rare. Depends on what's attached. The most common recognizable conformation of cyclohexane is a chair. We've alleviated angle strain, torsional, and steric strain by going to a chair from the planar form. But we have created 1, 3, 5 diaxial interactions above and below. So it's not totally problem-free. Now, that is your standard chair conformation. 6 equatorials, 3 axials above and 3 below. The ring can ring flip. At room temperature, this normally is not difficult. There's enough energy. At low enough temperature, well below 0, ring flip will not be able to occur because you have to have some external energy to allow a contortion. Now, I uploaded a video where I showed you molecular dynamics using Sci-Gress platform. And if you can do ring flip and contortions, you can get alternative conformations. There are many. For example, boat, twist boat, occasionally chair. The most common is the occasionally cyclohexane planar, and the common chair. Now you can do a ring flip. It's very important that you study this and understand it. This is how you do it. You grab 3 equatorials, 1, 3, 5, 1, 3, and 5. Bring them towards you. Hold them, bring them towards you. We just did a ring flip. Now it's very hard to tell when they're all hydrogens, but what was axial is now equatorial. What was equatorial is now axial. Now what I'm going to do is replace this hydrogen quite arbitrarily, and I'm going to place a red atom there. Let's suppose that represents a methyl group. Right now, that methyl group, the red one, and methyl occupies more space than hydrogen. Right now, the methyl group is in an axial position. If you were to build the ball and stick model and put a carbon with 3 hydrogens, you'd see that the hydrogens on that methyl would be very close to these axial hydrogens. We can't see it with a red atom, but the red would represent a methyl group. Now, another way I could do that would be, quite arbitrarily, I'll take this off, and I'm going to try to attempt to show you what happens here. Let this be a methyl group. Bear with me. Okay, I just happen to have these, so that'll give you an idea. Now, do you see what I mean? Here is your methyl carbon, and red, red, and blue would represent hydrogens of the methyl group CH3. As you rotate around that single bond, carbon in the ring and the methyl carbon, you see how close that can come to those axial hydrogens? Ouch, that's a bad thing. So what can we do here? Rule of thumb, you want to ring flip the chair so you get the maximum number of groups other than hydrogen equatorial. More breathing room. we're going to do a ring flip. Watch. 1, 3, 5. Bring them towards you. 1, 3, 5 hydrogens. Bring them towards you. We just did a ring flip. And do you know, now we have 3 hydrogens axial. And the methyl group is now equatorial, and there's more breathing room. Let me turn it this way. Do you see how much breathing room there? So rule of thumb, you don't break bonds doing a ring flip. It's a conformational isomerism. By ring flipping, you turn the ring inside out. What had been axial is now equatorial. And yes, the Boltzmann distribution, if you plug in a given temperature you're working at, it will tell you the energy difference between axial and equatorial if you were to plug in a value for a methyl group. And you'll find that about 95%, maybe 97% of the rings at room temperature with a methyl group will have the methyl in an equatorial position. Now watch. If you do a molecular dynamics with ball and stick model, 1, 3, 5, when I bring them towards me, that ring is going almost planar and then contorting in order to do a ring flip. And if you go through that very slowly, you can actually see that you're going through high energy intermediates to do a ring flip. And that's why at low temperature, there wouldn't be enough energy in the surroundings to allow that. It's just like pole vaulting. Let's do one again. Watch. 1, 3, 5, towards you or down. I'm going to push them down. We're going through. Do you see that? It's almost planar and then a boat. See, that's not a chair right now, but it will become one. There it is. So you want to put as many groups as possible, non-hydrogen groups, equatorial, without breaking bonds. Now, if you have a T-Butyl group, the T-Butyl group is the largest of the common groups you've studied. 99.5% of molecules at room temperature will have a T-Butyl group in an equatorial position. If you have a methyl and a T-Butyl on a ring, the T-Butyl gets first crack at equatorial. Now, there is a table at the end of the chapter. It's extremely important that you study it. 1, 2, we're talking about dimethyl cyclohexane. Just consider 2 methyl groups. Let me zoom in on this. I'll bring this down. Okay, dimethyl cyclohexane. Let's say 1, 2. We have one methyl group at the 1 position and the other at the 2 position of the ring. It turns out for 1, 2, the trans isomer is more stable than the cis. Now, how do you know what you have? Okay, watch. I'm going to remove this methyl group, and I'm simply going to go with a light blue atom representing a methyl. And then I'm going to make the ring planar, flatten it out. This is how you tell. Okay, so we have one methyl group right in the planar ring. Now I'm going to put a green atom, and I'm going to put it 1, 2, and I'm putting it into a trans position with this planar ring. Do you see that? When this is planar, the blue is up, the green is touching the page. 1 up, 1 down, that's trans, 1, 2 trans. Here, do you see them? There's the green down, there's the blue up. You see that easily with the planar ring. Now you know you have trans, pop it into a chair, 1, 3, 5. Right now you have a 1, 2 diaxial dimethyl. The methyl is an axial above, the green is an axial below. 1, 2 trans, a chair where the methyls are both axials. If we ring flip, 1, 3, 5, up or down, I'm going to push them down Ah, now you have a green equatorial and a blue equatorial. 1,2 diequatorial, which is trans. You write that down. Trans, double equatorial. That's the conformer that we prefer, where we have 1,2 trans diequatorial conformer, not diaxial. Now it turns out the cis will always have, for 1,2, an equatorial and an axial. There's no way you can get the cis isomer to have both groups equatorial. Now let me break a bond to convert the trans into cis. So I'm going to remove this and this. That's the only way you can convert them, is to break bonds. And you don't know how to do that yet. Okay. Now I'm going to put the green one there. And I'll put the hydrogen there. Now you don't know how to break those bonds yet chemically in the lab, but you'll learn that. Make it planar. We want a planar 6-membered ring. Do you see how they're both 1,2 cis? The blue and the green representing methyl groups. 1,2 cis. The same, 1,2 cis. We looked at trans already. All right, let's pop it into a chair. 1, 3, 5. The blue one is axial. The green one is equatorial. The green one is equatorial. The blue one is axial. See, it's near these two hydrogens. One there and one there. If you ring flip 1, 3, 5, you still get a green one axial and now a blue one equatorial, but they're both in opposite geometric fields. For 1,2 cis, you always have an equatorial and an axial conformer. So therefore, the winner there is the 1,2 trans, because that isomer can have a conformer with both methyl groups equatorial. Now it alternates, everyone. For 1,3, trust but verify. For 1,3, cis more stable than trans, because the cis will have a conformer double ec methyls. The trans will always have an equatorial and an axial. Trust but verify. Then 1,4, trans more stable than cis, because the trans will have a double ec, and the cis will have an equatorial and an axial. And then a 1,5. Let me move the paper up. And of course, I'll have videos, more of them, showing this using Sci-Gress. 1,5, cis more stable than trans. The cis has a double equatorial. Trans, equatorial, and axial. There's a table at the end of the chapter 3 which summarizes that. And then 1,6, well, 1,6, and you go around the bend and you're back where you started. And the 1,6 is going to be trans more stable than cis, which is 1,2, double equatorial. The cis is equatorial, axial. So you make sure you understand that. And with a ball and stick model, this is very easy to do, and it can really help with exams. But what I'm going to do is upload more videos showing you Sci-Gress and what I'm talking about here. Now, let me make this planar to finish. Right now it's 1,2 cis. Blue and green representing methyls, cis, same. 1,2. But I'm going to make it 1,3. So I'll break the green one. I'll put a hydrogen over there. I'll put a methyl then here, green. Now that's a 1,3. Can you see that the green one and the blue one, 1,3 cis. I'm going to go to a chair now from planar. There it's planar. Green, blue, cis, 1,3. I'm going to go to a chair. And right now I have a green axial and a blue axial. Ring flip, you get a winner. Green equatorial, blue equatorial. And that's why, going back to the chart, for 1,3, the cis is more stable than the trans isomer. See, these are geometric isomers, cis and trans. They can't be interconverted. Ring flip is conformational isomerism, or rotation around a carbon-carbon single bond. It can result in conformers. But these are geometric isomers, stereoisomers. They differ in 3D orientation and space and cannot be interconverted without breaking bonds. And that's why the 1,3 cis more stable than trans, because there's an equatorial there, green and blue. And let me zoom out. And you can then see the green and the blue are in equatorial positions. And that's why 1,3 cis more stable than 1,3 trans. 1,3 trans will always have one equatorial and one axial methyl group. It is important for you to understand the importance of studying conformational analysis, because in advanced molecular sciences touching upon synthetic biology and related fields, three-dimensionality, shapes, conformations, everything. It's everything. How well a drug binds to a receptor site will depend on the three-dimensional shape of the drug and its three-dimensional interaction with the three-dimensional receptor site. You'll learn this more and more as you go along, and those that study and do this early on are very wise. Thanks for watching. Bye for now, guys.